She was the head of the School of Mechanical, Industrial, and Manufacturing Engineering. She was an Air Force Office of Scientific Research Program Manager. She was an associate professor and a professor at Virginia Tech. So we're lucky to have this woman here running this program for us. Her research interests focus on computational methods, mathematical modeling, and the dynamics and control of autonomous vehicles and wave energy devices. So please give her a nice warm Science Pub welcome.
It's really a pleasure to be here with you guys tonight and talk about our latest passion, marine renewable energy at OSU. And anytime you've got a question, feel free to stop me in the middle, or you can wait till the end. I'm happy to take your questions and clarify anything that might not be clear already. I would like to thank Nick for the great welcome. We're about trying to use this to generate this so we can have more jobs like this and lots more of scenery like this. None of this and none of this. The end. Any questions? So I actually need to thank my colleague Jason Bush, the director of the Oregon Wave Energy Trust, for these slides. He gave this talk down at the South Coast in an economic development meeting. It went over really well, and I thought, that's it. That's it in a nutshell. So now let's delve into the details a little bit. I'm going to give you an introduction tonight to marine and hydrokinetic energy. That's a snazzy word for the energy that we're getting from the ocean. I want to talk a little bit about the kind of wave energy devices that are out there and that you might encounter in Oregon if you were to go out in the ocean and prowl around. And then I'm going to, since I'm a professor, I have to talk a little bit about the idealized models. So I'll do a little bit of idealized models and how they work. And I actually have a slide with a little bit of physics on it. Then I'm going to talk a little bit about NEMRIC. How did we come to be a leader in marine renewable energy? How did we come to be here at Oregon State? And I'm going to talk about the research of the fantastic faculty and students that we've got, and just give you a little snapshot of what we're doing. And then I'm going to talk about full-scale testing in Oregon. What's the future for us? What we're spending a lot of time doing. My program manager, Malia Ashford, is here, and I'll try and give you a sense of what might be coming in Oregon. So let's start out with the introduction to marine hydrokinetic energy. So when people talk about ocean energy, they're probably talking about one of these four approaches. We've got the wave energy, which is what we're focused on here in Oregon. We've got a phenomenal wave climate off the Oregon coast. There's tidal energy, capturing energy from the tides like you'd expect. That's actually what our University of Washington partner is focused on, tides in Puget Sound and how you get energy from that source. Current energy can be used to capture energy from something like the Gulf Stream. And so that's the third option there. And then the fourth is it's a marine energy, but it's not from the kinetics. It's from the ocean thermal gradients that you'll find. And there's some work going on with that in Hawaii. So generally, when you're talking about marine energy, it's going to be one of these four sources. There's another source that you'll find which is not always classified as marine energy. It's offshore wind. And they don't really classify as marine energy because energy from the winds, it just so happens that the devices are located in the ocean. So what kind of devices might you see? The pictures I've got here for you are of a device called the Oyster from a company called Aquamarine. It's sitting on the sandy bottom here, or actually it's probably kind of a rocky bottom. And the device goes back and forth like this as the ocean surges past it. They were talking about putting these in Oregon. One of the challenges one might find is the sediment transport off the coast might vary 10 to 20 feet during the winter. And so you'd have to do something to worry about how that sediment transport affects this part of the device. So you're probably more likely to see these devices on a rocky coast than you would on a sandy bottom. This device is called a limpet. It's called an oscillating water column. And as the waves rush up into it, it displaces air which goes through a turbine. The turbine spins, producing energy. As the waves go back out, reverse process happens. That's been in Islay in Scotland for about 8 years, I believe. This device is called Wave Dragon. It's called an overtopping device. The water will come up and go over the device and be captured, and then as the water goes back into the ocean, again, a turbine spins, producing energy. So this whole something happening in turbine spinning is a recurring theme. And then this device is called the Pelamis. It sits on top of the water. It goes like this as the waves go underneath, producing energy. This device is about, at least the current version of it is about 180 meters long, sitting on top of the ocean. The next slide I'm going to show you is all devices that are either in Oregon or that we're likely to see in Oregon. That doesn't mean we might not see these, but the other ones I can say in certainty we either have seen or will see. This is the Ocean Power Technologies device. You heard in your trivia quiz that OPT is going to be putting a device in Reedsport this summer. This device was a 40 kilowatt device that was in Hawaii at the test facility at Kaneohe Bay that's run by the Navy. And it was deployed for, I believe, 5 or 6 years. So they have some good information on that device. Again, this is 40 kilowatts. The ones going into Reedsport is rated at 150 kilowatts. This device is by Columbia Power Technologies. Anybody here from CPT tonight? The CPT is a local company. It's fun to go visit them because I can walk around the desks and see a bunch of Oregon State grads as you walk around. This device is interesting. It's got 2 floats on the side that go up and down like this as the waves go by, and it's got a central spar. So a lot of energy gets generated from these various motions. This device was in Puget Sound for about a little over a year, and they got a lot really good information about how it behaves. This device is a device that's sort of local. It's called M3. M3 comes from the owners, Mike, and Mike. Very creative. The story I like about this device is they were seniors in mechanical engineering at OSU, and I believe in '92. And they had this idea for a device. It had 2 bags, and as the waves went over top, there would be changes in the pressure in the water column that would push air from one device or one bag to the other bag and then back. And in the center was you got it, a turbine. And so they wanted to test this device for their senior project. This is really important. It's something you're graded on. And they knew that there was a wave tank in Graff that didn't work. It was owned by civil engineering. So they went over and talked to the head of civil engineering and said, hey, I want to test this project. I know the wave tank doesn't work. We'll test it. We'll fix the wave tank, test it, and empty it out, and you'll have a wave tank that functions now. And he said, no. So they broke into Graff Hall at midnight, fixed the wave tank. You know the story, fixed the wave tank, filled it up, put the device in, tested it. They still have video of this. Then they drained the water out, broke it the way it had been broken to begin with, and left. And 20 years later, these guys have a prototype that they tested in our facilities at Hinsdale, and they're actually a very promising technology that we have seen in Oregon under test. We're going to see more of them. And then this last device was the buoy that Nick mentioned that OSU tested in 2008. This was a joint project with Columbia Power Technologies. Prior to that, Dr. Von Juan, who Nick had mentioned, and her students had developed a device. So we have a history of wave energy technology in Oregon with OSU, and we're going to see more of this. So what does the wave resource look like worldwide? If you want to look for the really good spots, look for things in oranges and reds. You're going to find the best waves on the west side of the continent because the waves build as they go from west to east. So when they hit the west side of the continent, they're going to be at their biggest. That's the way the winds go. They're also at their biggest as you move away from the equator. So it's no surprise, based on thinking about that a little bit, that you're going to find good waves here, you're going to find good waves here, you're going to find good waves down here, here, and there. So when people talk about wave energy on the east coast of the U.S., I'd be a little suspect about that right now. Until devices get highly more efficient than they are right now, that's probably not where you're going to see them first. But in Oregon, we're in the sweet spot. And we also have a guest with us tonight from the European Marine Energy Center in Scotland. That's a place where they've been doing work in these device testing, device development for quite some time, and they're ahead of us. It's a pleasure to have him with us today. He's working with OSU on a project you'll hear more about in a little bit. So I want to talk a little bit now that you know generally what kind of devices are out there, where would you go to find wave resource. how do these things work? And the general rule of thumb is if you think about the fact that the ocean goes up and down, and it goes back and forth, and it goes side to side, anything you can think about that would take energy from those motions is the kind of thing that somebody might develop. So what I find talking to people most often, they think buoys. Certainly buoys are one of the ones that are out there. So how is a buoy going to work? So it's going to extract the energy primarily from this heave. Heave, that's the up and down motion is heave. The back and forth motion is surge, and then the side to side is sway. And so the device that we developed at OSU had this damper plate to try and keep it in place. The power takeoff was this magnet and coil system moving past each other. And then it had this buoy at the top. And so that motion back and forth is generating the electricity. And so if you're going to try and come up with a model, here's your physics. So for all these who are physics phobic, you can shut your eyes and cover your ears for a moment. Here's the equation across the top. In the frequency domain, you're going to have a force from the wave on the float. That's the excitation. Then when this thing moves back and forth in the waves, it creates its own radiative force right there. Then you've got a force due to the fact that the float is buoyant, a force due to your power takeoff, and this is your old mass times acceleration. So all this equation is force equals mass times acceleration. So you probably heard that in school at some point. So given that kind of model, you can use computational models, you can use programs that are out there that model the waves, model the device, you put it all together, and you can come up with some predictions for what your device is going to do in the water. And so this is a work of a graduate that we had named Kelly Rule, who now works for Sandia National Lab. And what you see here, she put in some wave data that she had from the buoys off the coast. And across the top here, you have the position of the spar plate, which you really wanted to stay in one spot, because that's trying to anchor things to give the buoy something to work against. And then in the kind of yellowish color, you've got the ocean height. And in the blue color, you've got the position of the buoy. So it's that motion of the buoy, the float, that's creating the energy. And you can see how it kind of follows what the ocean is doing. There's a slight delay, which isn't too surprising. And then there's places where the ocean does something really quick, and the buoy kind of evens it out. So not too surprising what you see, and you can use this information to come up with predictive ideas of how much energy should be produced. So again, when I'm out talking to the coastal community, talking to students, talking to audiences, a lot of times they seem to think buoys are the thing. But actually, this isn't the most efficient way you could get energy out, because it's really only extracting energy from that one motion. But there's other ideas that are out there. Another idea is the idea of a pendulum WEC. Now this device would sit on top of the ocean, and as the ocean moves back and forth and side to side, this thing is going to start moving around, and inside you've got a pendulum which would go around as well. So think about a self-winding watch, and how that motion of you going back and forth keeps the thing spinning. That would be the idea of this wave energy device. So one of the things about it that's interesting when students are looking at it is it can actually, the pendulum can stop at times, depending on what the ocean is doing. You know, it might get going around and then just get hitched up. And so some of the students at OSU are looking at control algorithms that you put on this to keep it moving. Actually injecting a little bit of energy might keep this pendulum spinning and produce more energy than if you just let it go on its own. So this would be another way you could look at getting energy from a device. Now in this picture, think about the wave coming in from this side, and what would be great is at the top of the wave if your pendulum was facing up. Because then as it's going down, your pendulum's going to drop, and now it's going to be in position for another wave to come in, and so then it can repeat the process and have the pendulum coming down again and being ready for the next wave input. So ideally, this is the kind of way you would, in an absolutely perfect wave, this would be the kind of thing you'd want your pendulum to do over that period of time to extract the most energy. Now obviously our waves aren't perfect, and hence you want these controls like I mentioned. Here's a slide, set of slides from a professor I know at the Air Force Academy in Colorado Springs. He's an aerospace engineer, and he had an interesting take on this whole thing. He called me up one day and said, you know, you guys are looking at this problem all wrong. You need to think about aerodynamics. I said, okay. And so here's the slide deck he gave me. So he said, think about the wave traveling from here to there. And now this, what's important to keep in mind about this is a perfectly sinusoidal wave, not like the waves we're going to find out in the ocean. If you had a wave energy converter, a wave energy device, that didn't do anything, and then when you turned it on, it actually generated waves that are equal and opposite to the wave that was there. Then, based on what you learned in school about waves, what should happen when these two things interact?
Cancel.
They should cancel. So that's what you would get. And so if you think about that, canceling means you're extracting all the energy out of that wave. So he said, what if I could design something that would do that? So his idea was, he's an aerospace engineer, I put an airfoil in the water and I move it along, and if I have it positioned right, it's going to create a wave. And then you can imagine the other piece of it. The other piece is, if you pitch it the other way, it'll create a trough. So he said, if I had these wings moving through the water, perfectly in sync with the wave that's coming in, I could cancel out waves. So what he did is came up with, okay, there's our wave travel direction again. And he's got a hydrofoil that's pitched in one direction and a second hydrofoil that's pitched in the other direction. They're connected by a shaft. The shaft turns around, and then as that happens, he's going to cancel out his waves. Now, I saw this experiment in a teeny little wave tank, and in his teeny little wave tank with a perfectly sinusoidal wave, he was actually canceling out 95% of the energy in that wave. So that was pretty impressive. And he thinks he's going to be able to do the same thing in the ocean. I'm a bit skeptical, but we'd like to help him test and see what really happens. So that's another kind of different way of looking at how you can get energy from waves. Okay, so now let's talk about NEMRIC. Let's talk about what we're doing at NEMRIC, why we're doing what we're doing, and where we're headed. So in 2008, the U.S. Department of Energy put out a funding opportunity announcement for proposals and said they wanted to create up to 3 marine renewable energy centers to focus on the problems that we talked about at first. So ocean current, ocean tidal energy, wave energy, ocean thermal. And they ended up funding 3 centers. The Southeast Center focuses on ocean current from the Gulf Stream, energy from the Gulf Stream, and ocean thermal. The Hawaiian Center is focusing on waves and ocean thermal. And then, as I mentioned before, we're focusing on wave and tidal. So the Department of Energy wanted us to facilitate device development. Now, when you talk about facilitating device development, that means we need to know how these devices produce energy. We need to know what kind of environmental effects they have. Effects on the physical environment, effects on the marine biology. How is the community going to react to these things? So when they talk about facilitate device development, there's a lot in there. So they're asking us to interact with the communities on this. And then they wanted us to inform regulatory and policy decisions. When you talked to the federal government about 3 years ago when this happened, we said we want to put a device out in the federal waters. All their regulatory policies are structured around oil and gas because that's what you put out there. They're thinking of drilling, they're thinking of extracting a resource that will never sort of regenerate itself. And so when you're talking about putting devices in the water that aren't really taking anything away, it was a really different way of looking at things. So we talk fairly often with these agencies about what we're finding and what their concerns are, and through this, policies are actually changing with respect to putting devices in the water. Close key gaps in understanding is a fancy way of saying we're a university, we do research, we educate graduate students, our faculty work on these. And of course, our job, the second side of our job at a university is to educate this generation of students that are going out into the community. And I mentioned this before, but it truly is a thrill to go through Columbia Power Technologies and see all our graduate students employed, graduated, doing exciting things in this emerging industry. So I do want to give a call out to the folks at OSU. All the folks on this list are faculty who are funded some way working on wave energy technology. And so you can see they span different areas in engineering, areas in oceanography, biologists at Hatfield Marine Science Center, Marine Resource Management, and Sea Grant. And so these are the folks who make it all happen. These are the folks who bring the projects together to advance this industry. So when I look at what we do at OSU, and the previous slide should have sort of alluded to this, we have three legs of the stool that we focus on: the technical side, the environmental side, and the social side. And this industry won't reach maturity without each of these three pieces. Simply understanding how they work technically is not going to ensure that they're safe to put in our waters. Simply ensuring that they're not going to hurt the biology is not enough to get the current community to engage. Fishermen are concerned that they'll lose fishing ground. I've heard people up in Tillamook saying, I don't want those things in my water. I don't want to see them every time I wake up and look outside. And hence that quiz question, are you going to see all devices above the water level? And the answer is no, of course. The M3 device is on the bottom. So one of the reasons why I believe OSU was competitive when the Department of Energy put out their call is because we have strengths in these three legs of the stool. And our faculty work together closely in collaboration to figure out where the intersections of these areas lie. So quick overview of some of the work going on at Hatfield. They want to know naturally what's going to happen to the marine biology when you put these things in the water. Where are they going to interact with the gray whales? If we want to put them in the areas where the gray whales will be, how do we keep the gray whales from being tangled in the moorings? They worry about things like acoustics. Are these devices so loud that they would get in the way of marine mammals communicating with each other? The mysid shrimp work is, mysid shrimp are a food source for whales. And so if the mysid shrimp are attracted to the devices, will the whales follow? So there's a variety of things that Hatfield's interested in, working on, trying to understand how these devices will interact. This is a problem on wave forecasting, and I apologize for this. There was a video here, and this video is the most cantankerous one I have, so I just gave up. But what this was is this is a picture of the world and the way the waves go across the world. This is a picture of the sort of upper northwest quadrant, and this is the west coast of the United States. And fundamentally, NOAA has buoys out that gather wave data, but they're pretty far off the coast. They're about 300 miles. And the information in these buoys is, the buoys are so coarse that it doesn't provide enough information to really do wave forecasting about where would you put devices, how would you operate them. And they're also a period of about 12 to 24 hours. So Tuba Ascan Haller at OSU did some computational work and developed predictive tools that, predictive tools that refine the mesh, refine the information so that you can get wave information all the way up and down the coast, very close into where we want to put these devices. And there's the difference between the real data and her predicted data. So she's doing very, very well on this. Her forecasts are up on NANU's website, which is an ocean information website. And even people like surfers get excited about this, being able to know 84 hours out when the good waves are coming. One of the big things most people who've heard about what we do, a lot of people hear about our testing. And so again, something we were really fortunate with at OSU, this wave tank here was put in the 60s. They didn't know that we'd be doing wave energy when they put this in, but this is an amazing resource. It's about 104 meters long, about 5 meters deep, and about 3 meters wide, and it's got a wave maker that can make waves that are so strong they'll pop out of the side of the tank. And so developers will come and they'll put their 1/15 scale device in there and get a good sense of what kind of energy it's producing, how their mooring systems will work, how it reacts to a 100-year storm. M3, who you've already heard about, was in there. Columbia Power Technologies has been in there. The second wave energy or wave tank that we've got, which is a real special asset, is known as the Tsunami Basin. People have heard about it in that context. It's more of a rectangular, or more of a squarish rectangular wave tank. It's got 29 paddles that'll operate independently, so you can do real wave profiles in this tank. And you can subject these devices to a real sea state. And so here's a picture of 5 of Columbia Power Technologies in the tank as an array to get an example of what kind of shadowing effects take place as you go past the first line of devices. And then this over here, you heard Nick talk about the WEC lab. That's the linear generator with a buoy on it. So you can put a sea state in there, move the buoy up and down with the sea state, and see what kind of energy is produced. So 5 different small-scale technologies came into our tank last year, and none of them was a buoy. So just to give you a sense that there's other things out there. One of the reasons people come to the tanks is not just because of the tanks themselves, but the testing capabilities we've got. The space system came out of the movie industry, and you can get sub-millimeter resolution here about the positions and velocities of these devices. So this allows people to gather data and validate the output of these devices with the predictive models that they've got. So once people have come and tested in these tanks, what's next? Well, you heard a little bit about our Newport test facility. So here is Yaquina Bay, and here is Yaquina Head, to give you 2 points of reference. And we started, actually not very long after we started the project, to develop this site, knowing that developers would have to go somewhere after using our tanks. They wanted to get out in the ocean. So we're working on permitting this site. It's going to be available year-round. We don't really anticipate many people will be testing year-round, because in the winter our resource is really tough. And while they might be, I'll give you a little bit more information about that. At first we expect they're going to be testing in the summertime. Two devices can test concurrently in there, and we've got 3 scenarios that people will be testing in that area with. So one would be, if somebody said, I really want to see what my device is going to do in the wintertime, we'd say, great, have at it. You can put your device in there, self-contained, maybe take all the information you need to gather the data from your device and stick it in your device, go ahead and moor it, and see how it does with the Oregon winter. The second way people can test is by connected to a ship. That's how we tested our buoy when we tested in 2008. And for a short period of time, in a buoy that's not going to produce too much energy, you could go out there and put your data acquisition devices and your load banks and all those kind of things on the back of the ship. The third way people will test, and we're planning on a test this summer this way, is connected to the Ocean Sentinel. So this schematic here is what we're calling the Ocean Sentinel. It's based on a NOAA Nomad buoy platform. That platform is about 6 meters long and about 4 meters wide. And inside it's going to have load banks, data acquisition devices, all the kinds of things you're going to need to take a device, and there's a schematic of my device, and connect it up through an umbilical. So we are planning toward having our first developer out there this summer. You'll be able to see both the developer's device and the Ocean Sentinel from Yaquina Head. You should be able to see it pretty easily. It's going to be this bright, obnoxious yellow that the Coast Guard makes us paint it. And these you will see above the top of the ocean. So at this point, developers are going to go out there. They can test this way, but it's not enough. We are limited to about 100 kilowatt devices with this test schematic. And so if a developer wants to test a utility scale device, which is half a megawatt, 750 kilowatts, a megawatt, something along those lines, there's currently no possibility to do so in the United States. So, full-scale testing today. If you want to test a device like that, you're going to head to Europe. And I mentioned that we've got Stuart Baird here from the European Marine Energy Center in the Orkney Islands, which is a phenomenal place to go. So while they've got a beautiful test site, and it's really excited to go there and spend some time on Orkney and try a little bit of their local scotch, the developers don't really get excited about transporting their device there. So they tell me 2 things. It costs a lot to transport. The other option is they could build the device there and test it. But they would like to have a supply chain here in the United States because they believe that they're going to be commercializing here. So the developers are very keen on having a test facility in the United States. So, U.S. Grid Connected Site. I'm going to tell you a story about this. About a year ago, I became the director of NEMRIC. And at that point, I knew this story, I knew where we were headed, I knew we wanted to have a grid connected site. And I went to a meeting in August, and U.S. Department of Energy stood up and said, I've got a great news for you guys. We're going to put our utility scale site in Kaneohe Bay, Hawaii. And so you can imagine my mood for the rest of the morning. So I started talking, why would you do this? Well, OPT had been in Kaneohe Bay, and the Navy has this mandate to be energy independent from the grid, and so they want to put a full-scale test facility out there, and the story went on and on and on. And so I went into full gear. I thought, okay, we need to do something about this. We need to show the U.S. Department of Energy why Hawaii is not the site for a full-scale site. Sure, it's great to get your feet wet, pun intended, and kind of kick the tires, but it's not going to serve the U.S. in terms of a utility scale site. So what I have for you here is Hawaii, and I've got 2 NOAA buoys there. I'm going to talk about wave climate is where I'm headed. And here's Alaska, and there's 2 buoys there. Here's Oregon with 2 buoys there, and California with 2 buoys there. So if you start looking at the average power produced at the buoys, here are the 2 buoys at North and East Oahu. Okay? So what happens when we look at these other buoys? There's the buoy at Newport, Oregon. Look at the difference in average power produced. There's the buoy at Bodega Bay, California, and Yucatan, Alaska. So the first case I made to the U.S. Department of Energy is if you put a device down in Hawaii, sure, it's great to get their feet wet, kick the tires, but it's not going to show what they're going to do and the kind of resource they'll be subject to when they're actually put in Oregon waters, Alaskan waters, California waters. Remember that wave resource picture I showed you? The second thing that I looked at was seasonal average power. I got kind of excited about this because then the DOE came back to me and said, oh, well, if we put the facility in Oregon, it'll rip their devices apart. We couldn't have that. What are we going to do? And so here's the Hawaiian average power over the year. So that's January to December, and you can see that buoy that's relevant are the 2 nearshore buoys. So you can see in the winter they're producing that, and in the summer they're here. Well, here's Oregon. The blue line is the one we're concerned about. And see in the winter, it produces a crazy amount of average power. So if you test in Hawaii, you're not going to have gone through this kind of regime. But the cool thing is that in the summertime, we're down here. We're down in the 10s to 20s, which is what you see here in Hawaii. So the story that was great for me was in Oregon, if you test in the summertime, you can have these calmer states, but you can really see what your device is going to do in the wintertime by coming here. And again, this is similar to what you're going to see in California and what you're going to see in Alaska. So, why Oregon for this grid-connected site? Well, we've got this big, vigorous resource that I just showed you where these devices need to be proven for utility scale. And in the summer, the guys who may not quite be ready for prime time can go in the waters. Another thing is if a device goes into Hawaii and you're interested in the environmental effects, there's a lot that you can't extrapolate from there to here. They don't have Dungeness crabs in Hawaii. What's going to happen with that? We've got different whale populations, different mammal populations. So while you may be able to get some information about how your device behaves, you're not going to be able to have the environmental data that you're going to need to go through the regulatory process. We have manufacturers here in Oregon who are already to step up and make these devices. Oregon Iron Works, American Bridge, Christensen Yachts, a lot of smaller people who are willing to get engaged, ready to get engaged. And so when the developer said to me, I'd like to set up supply chains that I can use for testing and for commercial development, this could mean really great things for the state of Oregon. And then the last point here, why you might move to Oregon, is we've got strong state support. The governor just came out with ocean energy and his 10-year energy policy. The state has set up the Oregon Wave Energy Trust. And then we've got OSU, who's been interested in this area for quite some time. And I think that the value in having OSU and NEMRIC is that we're the neutral voice of science. You need to have that voice there in the midst of all this, not just pushing it blindly, but being able to say to the user community, like the fishermen, we tested this device. This device seems like it's really going to be good for our environment. We tested that device. The acoustic emissions really aren't what you're going to want for the fishing populations. So, what's NEMRIC's future here in Oregon? Well, we're expanding our research activities not just to be WAVE and our partners at University of Washington and Tidal, but we're working toward offshore wind. There's a project that people want to site in Oregon off the coast about 10 to 12 miles. They're floating platforms, so you have a tidal turbine on top of a floating platform, and sometimes these floating platforms might have wave energy devices integrated into the platform. So it's a really neat opportunity for us to get engaged and take what we know already into this new area. You'll see NEMRIC continuing to developer support. We not only have them come into our wave tanks and test, but sometimes we get involved in joint research projects. We might get involved in research projects about the materials that they use or the bearings that they use, or I mentioned a little bit about some control algorithms. And so that's a really great place for our students to get their hands dirty on a real-life project and not just a computer project or a paper pencil project. And then, as I mentioned, we plan to have the Newport Open Ocean Test Facility going this summer. Drive along the coast, we see that yellow thing out there, you'll be able to tell somebody, hey, I know what that is. Something I'm really engaged in right now is developing this grid-connected test facility. It looks like U.S. Department of Energy understands the story. They gave us an opportunity to develop a project that's a total of $8 million to start working on this grid-connected test facility. That's just the tip of the iceberg. We estimate that the test facility is going to cost somewhere around $25 million. So you can imagine, you know how much money the state of Oregon has, so they're not coming to me with big bags of money. So I'm working a lot trying to look for private investment, which is not really what I thought I'd be doing as a mechanical engineering professor. But that's the reason why Stuart's here with us today, is we're using EMEC's knowledge about not only putting together a test facility, but operating a test facility to help us on site selection. So we've identified 4 sites where the test facility might go. One is up by Camp Rylea, one is at Newport, one is at Reedsport, and one is at Coos Bay. The reason we didn't just go with our current Newport site is it's a bit shallower than these utility scale devices will need. So we're going through the site selection process. We're working on coastal outreach. In fact, I'm going to Coos Bay tomorrow to talk with fishermen and port commissioners about what the site might look like in their community. And so as the year evolves and as the coming years come, I firmly believe that we will be developing such a site in Oregon, which will be the only utility scale site in the United States. Very exciting opportunities. And then lastly, NEMRIC will continue to provide the scientific perspective to stakeholders. While I believe that this technology has a promising future in Oregon, it is really important as Oregon State University to be representing the marine biology, the physical effects, the social side, and the technology all together. So you can count on us to present those perspectives to the stakeholders. So I want to thank you for your attention. We've got my contact information there. You can find us on OSU's website. Feel free to give us a call, send us email if you've got questions. It's really been a pleasure to be here tonight and tell you about what's going on.